Today, I'm going to read the chapter Thermochemistry of Physical Chemistry from the book Pradeeps, written by Dr. S.C. Khetrapal. 1.19 Thermochemistry General Introduction. All chemical reactions as well as a large number of physical changes are accompanied by evolution of absorption of energy, generally in the form of heat, that is, energy is transferred from the system to the surrounding or vice versa. The branch of chemistry which deals with the energy changes such as heat, light, energy, etc. accompanying chemical reactions is known as chemical energetics. The restricted branch of chemistry which deals with the study of heat changes accompanying chemical reactions is known as thermochemistry. The reactions which are accompanied by evolution of heat, that is, in which heat is transferred from one system to the surrounding, are called exothermic reaction, whereas the reactions are accompanied by absorption of heat, that is, in which the transferred from the surrounding to the system, are called endothermic reactions. As reactions are generally carried out in open vessel, that is at constant pressure equal to atmospheric pressure, and the heat changes at constant pressure are expressed in terms of enthalpy changes. Therefore, the heat evolved or absorbed are expressed in terms of enthalpy change, delta H. But delta H reaction is equal to sum of enthalpies of product minus sum of enthalpies of reactant. Now, as in exothermic reaction, heat is evolved. Summation of H reactants must be greater than summation of H products. Hence, delta H for exothermic reactions is negative. Similarly, for endothermic reactions, as heat is absorbed, summation of H reactants must be less than the summation of H products, and therefore delta H for endothermic reaction is positive. Hence, taking a few examples for exothermic reactions, we write CH4 gas plus 2O2 gas is equal to CO2 gas plus H2O gas plus 890.4 kJ per mole. CH4 gas plus 2O2 gas is equal to CO2 gas plus 2H2O gas. Delta H is equal to minus 890 kJ per mole. Second, H2 gas plus half O2 gas is equal to H2O liquid plus 285.8 kJ per mole. Here delta H is minus 285.8 kJ per mole. Similarly, taking a few examples of endothermic reactions, we can write first H2 gas plus I2 gas is equal to 2HI gas minus 52.5 kJ per mole. Here delta H is equal to plus 52.5 kJ per mole. Second, N2 gas plus O2 gas is equal to 2NO gas minus 180.7 kJ per mole. Here delta H is equal to plus 180.7 kJ per mole. 1.19.2 Standard state. The molar enthalpy of any substance depends on pressure and temperature. That is, it is the function of pressure and temperature. If every reactant and product is taken at 1 atmosphere and at a temperature of 298.15 Kelvin, the enthalpy change accompanying the reaction is called a standard enthalpy change of the reaction. It is represented by delta H naught. These conditions, that is 1 atmospheric pressure and a temperature of 298.15 Kelvin, are the standard state conditions. As absolute value of molar enthalpy of any substance can be determined, hence the following convention is used to find out the standard molar enthalpy of any substance. The standard molar enthalpy of any element that is at 1 atmospheric pressure and 298.15 Kelvin in the most stable state is taken as 0. For example, the most stable form of hydrogen in gaseous H2. That of bromine is liquid bromine, while the iodine is solid I2. Hence, the standard molar enthalpies, that is at 1 atmospheric pressure and 298.15 Kelvin, are taken as 0. In case of elements exhibiting allotropy, 0 value is assigned to the form which is most stable of the atmosphere at the atmospheric pressure. That is, for example, graphite, note the diamond. Rhombic sulfur, not monoclinic sulfur. The above convention help us to calculate the standard molar enthalpy of any compound as explained below. Half H2 gas plus half I2 solid is equal to HI gas. Delta H naught of reaction is equal to summation of H naught of products minus summation of H naught of reactants is equal to H naught of HI minus half of H naught H2 plus half of H naught I2. But the standard enthalpy change of the above reaction is the standard enthalpy of formation of HI, as defined in the next section, represented by delta HF naught. Hence, delta HF naught is equal to delta naught HI. Thus, the standard enthalpy of the compound is equal to its standard enthalpy of formation. Standard enthalpy of formation. The standard enthalpy of formation of a compound is defined as the enthalpy change accompanying the formation of 1 mole of the compound in the standard state from its elements, also taken in the standard state. It is represented by delta HF naught. For example, for the formation of 1 mole of CO2 from its elements, we have carbon solid plus O2 gas is equal to CO2 gas. Delta HF naught is equal to minus 393.5 kJ per mole. Similarly, for the reaction 2H2O gas plus O2 gas is equal to 2H2O gas. Delta H naught is equal to minus 571.6 kJ. So that the formation of 1 mole of H2O, we have delta HF naught for water is equal to minus 571.2 divided by 2 is equal to minus 285.8 kJ per mole. Importance of standard enthalpies of formation. Knowing the standard enthalpies of formation, different reactants and products, and applying the convention that the standard enthalpies of formation of elements in their most stable state are taken as 0. The enthalpy change for the reaction can be calculated as follow. Delta HF naught is equal to delta HF naught of products minus summation of delta HF naught of reactants. Example is given. Calculate the standard enthalpy of combustion of methane. Given that the standard enthalpies of formation of CO2 gas, H2O liquid and CH4 gas are minus 393.5, minus 285.8 and minus 74.9 kJ per mole respectively. Solution. For the combustion of 1 mole of methane, the balanced equation is CH4 gas plus 2O2 gas is equal to CO2 gas plus 2H2O liquid. Delta RH naught is equal to summation of delta HF naught products minus summation of delta HF naught reactants. That is delta RH naught is equal to minus 890.2 kJ per mole. Standard enthalpy of combustion. The standard enthalpy of combustion is the amount of heat evolved or absorbed when 1 mole of the substance under standard conditions is completely burnt to form the products under standard conditions. It is represented by delta CH naught. For example, when 1 mole of methane is completely burnt, the reaction is CH4 gas plus 2O2 gas is equal to CO2 gas plus 2H2O gas. Delta H naught is equal to minus 890.4 kJ per mole. Hence, standard enthalpy of combustion of CH4, that is delta CH naught is equal to minus 890.4 kJ per mole. It is important to note that it is not the combustion that is taking place at 298 Kelvin, which in fact cannot happen. It is the total enthalpy change that occurs when the initial reactants and final products are at 298 Kelvin, irrespective of the fact that during combustion temperature is higher than 298 Kelvin. Enthalpy of neutralization. The enthalpy of neutralization of an acid by a base is defined as the enthalpy change, usually the heat evolved, when 1 gram equivalent of the acid is completely neutralized by the base, the reaction being carried out in dilute aqueous solution. The enthalpy of neutralization of a base by an acid is defined in a similar manner. For example, when 1 gram equivalent of HCl is neutralized by NaOH or 1 gram equivalent of NaOH is neutralized by HCl, both solutions being dilute and aqueous, 57.1 kJ of heat is produced. Thus, we may write NaOH plus HCl is equal to NaCl plus H2O. Delta H is equal to minus 57.1 kJ per mole. Hence, the enthalpy of neutralization of HCl with NaOH or NaOH with HCl is 57.1 kJ. The enthalpy neutralization of a strong acid, that is HCl, HNO3, H2SO4 with a strong base, LiOH, NaOH, KOH or vice versa, is always the same, that is 57.1 kJ. This is because the strong acid, strong bases and the salts that they form are completely ionized in dilute aqueous solution. Thus, the reaction between any strong acid and strong base, for example, in the above case may be written as Na positive plus OH negative plus H positive plus Cl negative is equal to Na positive plus Cl negative plus H2O. Delta H is equal to minus 57.1 kilojoule per mole. H positive aqueous plus OH negative aqueous is equal to H2O liquid. Delta H is equal to minus 57.1 kilojoule per mole. Is neutralized by HCl. Both solutions being dilute and aqueous. Thus, neutralization is simply a reaction between the H positive ions given by the acid with the OH negative given by the base to form a molecule of H2O. Since strong acids and strong bases ionize completely in dilute aqueous solution, the number of H positive ions and OH negative ions produced by 1 gram equivalent of the strong acid and the strong base is always the same. Hence, the enthalpy of neutralization between a strong acid and a strong base is always constant. In case either the acid or the base or both are weak, the enthalpy of neutralization is usually less than 57.1 kilojoule. The reason for this may be understood by considering the neutralization of a weak acid like acetic acid with a strong base like NaOH. Acetic acid ionizes small extent whereas NaOH ionizes completely, as CH3COOH is converted into CH3COO negative plus H positive. Second, NaOH is converted into Na positive plus OH negative. When H positive ions given by the acid combine with OH negative ions given by the base, the equilibrium first shifts toward the right. That is, more of acetic acid dissociates. A part of the heat produced during the combination of H positive ions and OH negative ions is used up for the complete dissociation of acetic acid. The heat thus used up is called enthalpy of dissociation or enthalpy of ionization. It is 1.9 kilojoule for acetic acid. Hence, the net heat evolved is about in the reaction is 57.1 minus 1.9 is equal to 55.2 kilojoule. Similarly, in the neutralization of NH4 with HCl, 5.6 kJ of heat is used up for the dissociation of weak base, that is NH4OH. Hence, the enthalpy neutralization in this case is only 57.1 minus 5.6 is equal to 51.5 kJ. It is important to mention here that heat of neutralization is taken for 1 gram equivalent of the acid and base. This is because the neutralization involves combination of 1 mole of H positive ions with 1 mole of OH negative ions to form 1 mole of H2O. 1 gram equivalent of an acid on complete dissociation gives 1 mole of H positive ions, but 1 mole of an acid on dissociation may not give 1 mole of H positive ions. For example, 1 mole of H2SO4 gives 2 moles of H positive ions on complete dissociation. However, 1 gram equivalent of H2SO4 gives 1 mole of H positive ions. Hess law constant heat summation. G.H. Hess, a Russian chemist, in 1840 gave a law about the heats of reactions on the basis of experimental observations. This law is known after his name as Hess law. It states as follows. The total amount of heat absorbed or evolved in a reaction is the same whether the reaction takes place in one step or in number of steps. In other words, the total amount of heat in a reaction depends only upon the nature of the initial reactants and the nature of the final products, and is independent of the path or the manner by which this change is brought about. Thermodynamic basis of Hess law. As heat content is the state function, therefore enthalpy change during the reaction depends only on the nature of initial reactants and that of the final products, and does not depend upon the path by which the change is brought about. Theoretical proof of Hess law. Consider the general reaction. A is converted into B. Suppose the heat evolved in this reaction directly is capital Q joules. Now suppose the same reaction takes place in 3 steps as follows: A to B, B to C, C to D. Suppose the heat evolved in these 3 steps are small q1, q2, q3 joules respectively. Thus, the total heat evolved is equal to q1 plus q2 plus q3 is equal to capital Q dash joules. Say, according to Hess law, we must have Q is equal to Q dash. If Hess law were not correct, then either Q dash is less than Q or Q dash is more than Q. Suppose Q dash is more than Q. This meant that if we go from A to D in number of steps, the heat evolved is more than the heat absorbed when we return from D to A directly in one step. Remember that for the direct process A to D, Q joules of heat is evolved. So for the reverse process with D to A, Q dash joules of heat will be absorbed. Thus, the cyclic process is completed. Q minus Q dash joules of heat is produced. This means that by repeating the cyclic process a number of times, a large amount of heat can be created. This is, however, against the law of conservation of energy. Hence, Q must be equal to Q naught. That is, Hess law must be correct. Applications of Hess law. The most important application of Hess law is in the calculation of heat changes for those reactions for which experimental determination is not possible. The calculations are based upon the following consequences of Hess law. The thermochemical equations can be treated as algebraic equations which can be added, subtracted, multiplied or divided. A few important applications of Hess law are given below. First, calculation of enthalpy of formation. The enthalpies of formations of many compounds cannot be determined experimentally. These are calculated by the application of Hess law. The following examples illustrate the method. Second, calculation of enthalpy of allotropic transformations. Elements like carbon and sulfur exist in different allotropic forms. The change of one form to the other involves a very small amount of heat and is a very slow process. Hence, the experimental determination of heat changes for the transformation is very difficult. These are calculated by the application of Hess law as illustrated by the example given below. Example, calculate the enthalpy change accompanying the transformation of C graphite to C diamond. Given that the enthalpies of combustion of graphite and diamond are 393.5 and 395.4 kilojoule per mole respectively. Solution. We are given first carbon graphite plus O2 gas is equal to CO2 gas. Delta H is equal to minus 393.5 kilojoule per mole. Second, carbon diamond plus O2 gas is equal to CO2 gas. Delta H is equal to minus 95.4 kilojoule per mole. We aim at graphite to carbon diamond. Subtracting equation 2 from 1, we get delta H is equal to 1.9 kilojoule per mole. Third, calculation of enthalpy of hydration. The experimental determination of the enthalpy of hydration is almost impossible. However, it can be easily calculated by using Hess law as illustrated by the following example. 4. Predicting the enthalpy change of any reaction. Hess law can be applied to predict the enthalpy change for any reaction from the enthalpy changes to certain other reactions. The numerical problems given below will illustrate the application of Hess law. Relationship between heat of reaction at constant volume and at constant pressure. According to first law of thermodynamics, delta U is equal to Q plus W is equal to Q minus P del V. W experimental is equal to minus P delta V, or Q is equal to delta U plus P delta V. If during the reaction the volume remains constant, delta V is equal to 0. Hence, QV is equal to delta U. That is, heat of reaction at constant volume is equal to internal energy change. However, if the reaction takes place at constant pressure, QP is equal to delta Q plus P del V. QP is equal to del H. Delta H is equal to delta Q plus P delta V. Hence, the reaction at constant pressure is equal to the enthalpy change. Putting delta V is equal to V2 minus V1 in equation 2 can be written as QP is equal to delta U plus P bracket V2 minus V1, that is delta U is equal to PV2 minus PV1, where the initial volume of V2 and the final volume, where V1 is the initial volume and V2 is the final volume. But the ideal gas PV is equal to nRT. So that we have PV1 is equal to N1 RT, PV2 is equal to N2 RT, where N1 is the number of moles of gaseous reactants and N2 is the number of moles of gaseous products. Substituting these values in equation 3, we get delta H is equal to delta U plus N2 RT minus N1 RT is equal to delta U plus bracket N2 minus N1 RT. Delta H is equal to delta U plus delta NG RT. Where delta Ng is equal to N2 minus N1 is the difference between the number of moles of gaseous product and those of the gaseous reactants. Putting the values of delta U from equation 1 and equation 6 becomes Qp is equal to Qv plus delta Ng RT. Conditions under which Qp is equal to Qv or delta H is equal to delta U. First, when reaction is carried out in a closed vessel so that volume remains constant, that is delta V is equal to 0. Second, when reaction involves only solids or liquids or solutions but no gaseous reactants or products. This is because the volume changes of the solids and liquids during a chemical reaction are negligible. Third, when reaction involves gaseous reactants and products but their number of moles are equal, that is Np is equal to Nr. For example, in the reactions H2 gas plus Cl2 gas is equal to 2HCl gas. Carbon solid plus O2 gas is equal to CO2 gas. Thus, Qp is different from Qv only in those reactions which involve gaseous reactant and products, and Np gaseous is not equal to Nr gaseous. Note: heat of combustion is found using a bomb calorimeter, that is, in a closed vessel, hence volume remains constant, that is delta V is equal to 0, and form the relation delta H is equal to delta U plus P delta V. We should have delta H is equal to delta U or Qp is equal to Qv. However, this is not true because the relation delta H is equal to delta U plus P delta V holds good only at constant pressure. This may be seen as follows: H is equal to U plus PV, delta H is equal to delta S U plus P delta V plus V delta P. At constant pressure, delta P is equal to 0. Hence, delta H is equal to delta U plus P delta V. At constant volume, delta V is equal to 0, hence delta H is equal to delta U plus delta P delta V. Bond enthalpy or bond energy. We know that energy is involved when a bond is formed and energy is required for the dissociation of a bond. Hence, bond energy is defined as follows. Bond energy is the amount of energy released when 1 mole of the bonds are formed from the isolated atoms in the gaseous state, or the amount of energy required to dissociate 1 mole of bonds present between the atoms in the gaseous molecules. For diatomic molecules like H2, O2, N2, Cl2, HCl, HF, etc., the bond energies are equal to their dissociation energies. For polyatomic molecules, the bond energy of a particular bond is not the same when present in different types of compounds. For example, bond energy of carbon with bond with Cl is not same as CH3Cl, CH2Cl2, CHCl3, CCl4. In fact, the bond energy of a particular type of bond is not same even in the same compound. That is, in CH4, the bond energy for the first, second, third and fourth CH bond are not equal, their values being 427, 439, 452, 347 kJ per mole respectively. Hence, in such cases, an average value is taken. Thus, average CH bond energy is equal to 416 kJ per mole. The most accepted value of the bond energies of some common bonds are given in the table. Calculation of bond energies. For polyatomic molecules, the bond energy of a particular bond is found from the values of the enthalpies of formation, which in turn may be obtained from enthalpies of combustion, enthalpies of sublimation, enthalpies of dissociation, etc. Similarly, the bond energies of heteronuclear diatomic molecules like HCl, HF, etc. can be obtained directly from experiments or may be calculated from the bond energies of homonuclear diatomic molecules. These calculations are illustrated in the following examples. Variation of heat of reaction with temperature, that is Kirchhoff's equation. It is found that the heat evolved or absorbed in a reaction depends upon the temperature at which the reaction is carried out. The exact relationship showing the variation of heat of reaction with temperature was given by Kirchhoff's in 1858 and hence is known as Kirchhoff's equation. It can be derived as follows. Case 1. When the reaction is carried out at constant pressure, consider the general reaction. A reactant converted into B product. Suppose HA is the total heat content of the reactants and HB is the total is of the products at the same temperature and pressure. Then the enthalpy change accompanying the reaction will be given by delta H is equal to HB minus HA. Differentiating the equation with respect to temperature T, pressure remaining constant, we get del H divided by del T at constant pressure is equal to del HB divided by del T at constant pressure minus del HA divided by del T at constant pressure. But according to the definition of heat capacity at constant pressure, we know that Cp is equal to del H divided by del T at constant pressure. Del HB divided by del T at constant pressure is equal to Cpb and del HA divided by del T at constant pressure is equal to Cpa, where Cpb is equal to mean molar heat capacity of the products at the given pressure. Cpa is equal to mean molar heat capacity of the reactants at the same pressure. Putting these values in equation 1, we get delta H divided by del T at constant pressure is equal to Cpb minus Cpa. But Cpb minus Cpa is equal to delta Cp is the change in the heat capacity when reactants change into products at constant pressure. Hence, delta H divided by delta T at constant pressure is equal to delta Cp. Further, since the term delta H is used for the heats of reaction at constant pressure, therefore the equation can be given by simply put as delta H divided by delta T is equal to delta Cp. This equation is only for a small temperature difference, dt. For large temperature differences, suppose of delta H at T1 is equal to delta H1 and value of delta H at T2 which is more than T1 is equal to delta H2. Then integrating equation 3 between the limits we have integration of delta H1 to delta H2 d delta H is equal to delta Cp dt from integrating T1 to T2. Delta H2 minus delta H1 is equal to delta Cp bracket T2 minus T1, where Cp has been assumed to be constant in the temperature range T1 to T2. Equation 4 may be written in the form delta H2 minus delta H1 divided by T2 minus T1 is equal to delta Cp. This equation is known as Kirchhoff's equation and may be expressed in words as follows. The change in the heat of reaction at constant pressure for every degree change of temperature is equal to the change in the heat capacity at constant pressure accompanying the reaction. Equation 5 is useful in calculating the heat of the reaction at given temperature when it is known at another temperature. Alternative derivation. Consider the general reaction A to B. Suppose the heat of reaction heat evolved at temperature T1 is equal to delta H1 and the heat of reaction heat evolved at temperature T2 is equal to delta H2. Now starting from A at temperature T1, we can obtain B at temperature T2 by two different paths as shown in figure. Path 1, we may allow the reaction to take place at temperature T1 to obtain B at the same temperature and then heat it up to the temperature T2. Then heat evolved in the first stage is equal to delta H1. Heat absorbed in the second stage is equal to Cpb bracket T2 minus T1, where Cpb is the average molar heat capacity of the products. Net heat evolved is equal to delta H1 minus Cpb into T2 minus T1. Path 2. We may first heat up the reactants to the temperature T2 and then allow them to react to give the products at the same temperature. Then, if Cpa is the average molar heat capacity of the reactant A, heat absorbed in the first stage is equal to Cpa into T2 minus T1. Heat evolved in the second stage, delta H2 supposed above, net heat evolved is equal to delta H2 minus Cpa into T2 minus T1. Now, since the initial and the final stages are the same in both the above cases, therefore, by the law of conservation of energy or by Hess law, we must have net heat evolved by path 1 is equal to net heat evolved by path 2. Delta H1 minus CPB into T2 minus T1 is equal to delta H2 minus CPA T2 minus T1. Delta H2 minus delta H1 divided by delta T2 minus T1 is equal to delta CP, which is the same as derived by the first method. Case second, when the reaction is carried out at constant volume. We know that delta H is equal to delta U plus P delta V. Under the conditions of constant volume, delta V is equal to 0. Delta H is equal to delta U. Hence equation 5 derived above takes the form delta U2 minus delta U1 divided by T2 minus T1 is equal to delta CV, where delta CV is equal to CVB minus CVA is the change in the heat capacity at constant volume accompanying the reaction. CVA and CVB are the mean molar heat capacities at constant volume of the reactants and the products respectively. Delta U1 and delta U2 are the internal energy changes, that is heat of the reaction at constant volume when the reaction is carried out at temperatures T1 and T2 respectively. Thus, Kirchhoff's equation may also be expressed as follows. The change in the heat of reaction at constant volume for every degree change of temperature is equal to the change in the heat capacity at constant volume accompanying the reaction. Thank you.